Exercise 2. Develop a math model for the following problem. If the model is a linear programming problem, solve it manually and interpret the solution. Okay. A metal fabrication shop makes two types of window security grills: standard design and deluxe design. The standard design is a plain design consisting of horizontal and vertical steel bars. The deluxe design has additional ornamentation and a quick release system for emergency escape. A standard design sells for $50, while a deluxe design sells for $90. The fabrication of a standard design entails 22.5 minutes of fitting, 10 minutes of welding, and 10 minutes of painting. The fabrication of a deluxe design entails 60 minutes of fitting, 20 minutes of welding, and 15 minutes of painting. The shop employs 5 full-time and 1 part-time fitter, each respectively working 8 and 6 hours per day. The shop also employs 2 full-time welders, each working 8 hours per day, and 4 part-time painters, each working 3.5 hours per day. Assuming everything produced is sold, what should the daily production of window security grills be in order that the maximum sales revenue is achieved? All right. The first variables that come to mind here, most obvious ones, would be to let X be the number of standard design grills to fabricate. And similarly, Y could be some ditto marks here, the number of deluxe design grills to fabricate. Okay, the actually key quantity in this question is the sales revenue. So let's bring in perhaps R for that. R is revenue. And let's go ahead and formulate that. The revenue would come from 2 sources. Revenue from sales of the standard design. One standard design sells for $50. Okay, so if we have X of them, we have 50X revenue from that. And then there's the revenue from the deluxe design, one of which sells for $90. 90Y will be the total revenue from Y of them. Okay. Now let's see. This would be our objective function. Kind of important. Okay. Now X and Y. There's some restrictions here, so this leads us to a subject to consideration. Alright, what have we got? Well, first of all, let's just talk about physical sense here for a minute. You can't very well fabricate a negative number of grills. That being the case, physical sense would dictate that X greater than or equal to 0 and Y greater than or equal to 0. Another consideration could be that X and Y need to be integers. Well, let's see. Yes and no. I guess it's kind of a subjective call here. If you consider a partial fabrication for the day as being okay, maybe you finish it up the next day. In other words, you get the standard design all fit up, but not yet welded and painted. Maybe you can allow for something like that. Okay, so maybe it could go either way on this consideration. Let's just leave it as allowing for partial fabrications as being allowable in our formulation here. Okay, then in addition to physical sense, we have got some other things to worry about here. There's some fitting labor involved in creating each of these 2 designs, and there's only a limited amount of fitting labor available. Okay, so another kind of bullet here, and we could say available fitting labor. Okay, how can we formulate that? The standard design, 22.5 minutes of fitting. Okay, alrighty, consideration here. Do we want to think about time in terms of hours or minutes? It's true the fabrication details are in terms of minutes. The labor is in terms of hours. The numbers seem to be heading towards rather large numbers if we deal with minutes. The kinds of minutes involved in the formulation actually convert very easily to hours, fractional hours here. 10 minutes, 1/6 of an hour. 20 minutes, that's 1/3 of an hour. All fairly simple numbers here. Okay, the 22.5, first it looks a little messy, but wait a minute. 15 minutes is a quarter hour. Half of 15 is 7.5. 15 plus 7.5 is 22.5. This is actually 3/8 of an hour. Okay, let's just go with the hours idea. It looks pretty good. Now, for available fitting labor, we can take the amount of time needed to fit one standard design. Okay, 22.5 minutes. That's 3/8 of an hour. Consider you've made X of these during the day. You need to do the 3/8 times X. And now let's consider the deluxe design. It says the fabrication of a deluxe design entails 60 minutes of fitting. Okay, that's 1 hour. And that has to be less than or equal to the available fitting labor. Let's look here. The shop employs 5 full-time and 1 part-time fitter, each respectively working 8 and 6 hours per day. Okay, 5 full-timers at 8 hours a day. 5 times 8 plus 1 part-timer working 6 hours. Okay, by the way, this sums to 40 and 6, 46 there. Okay, and we may decide that, okay, to organize things, let's say here's inequalities number 1. This could be inequality 2. Let's maybe get rid of this fraction here. Multiply both sides by 8. And we could rewrite this then as 3x plus 8y less than or equal to 8 by 46. Okay, up here. 8 by 46. There's a 48. Bring 4 up there. There's 32, 36. Okay, 368. And we could call this 2a since it's derived from the fundamental number 2. Okay. Okay, having considered the fitting labor, a similar consideration would have to be the available welding labor. Okay, another bullet here. Available welding labor. Alright, let's see. When we fabricate a single standard design, 10 minutes of welding. Okay, that's 1/6 of an hour. Now that's for one. If you make X of them, 1/6 times X is the labor to do that. As far as the deluxe designs, what have we got there? Deluxe design, 20 minutes of welding. Okay, that's 1/3 of an hour. So that's 1/3 of an hour for 1/3 times Y, the labor to weld all Y of those. And this has got to be less than or equal to, what kind of welding labor has this shop got? It has 2 full-time welders, each working 8 hours per day. Okay, so there's 2 welders at 8 hours a day. That would be 16 there. Okay, here's inequality 3. And perhaps we clear the fractions here, multiply both sides by 6. And this could be rewritten as x plus 2y less than or equal to 6 by 16, 96. Okay, here could be 3a. Alright, let's see. Painting. There's only so much painting labor. So here, available painting labor. Alright, let's see, what have we got? The standard design requires 10 minutes of painting. That's 1/6 of an hour for 1/6 times x for all the painting labor for standard design for a day. The deluxe design, 15 minutes of painting. Okay, it's a quarter hour. That's for 1. If we made y, then 1/4 times y for total deluxe design painting for the day. And that's got to be less than or equal to, what kind of labor have we got available for painting? It's 4 part-time painters, each working 3.5 hours per day. Okay, 4 painters at 3.5. Okay, that would be 14 in other words. We may decide to clear these fractions by multiplying both sides by 12. And that would give us 2x plus 3y less than or equal to 12 by 14. 12 by 12 is 144. Add 24 more to that, 168. Okay, so this is a fundamental inequality number 4. This we derived from it. We can call this 4a. And it looks like we've now accounted for everything in the question as far as restrictions for x and y. What kind of math problem is this? Now looking back over at it, we are to, oh, by the way, we're trying to maximize revenue. Right? Okay, so this is an optimization question. The objective function is, with this formulation, it's linear. And if we look at all of these constraints, each is linear. Okay, so what we have now is this is a linear programming problem. Alright, so our basic strategy would be to get the graph of this domain or feasible region and locate the vertices, and then we can calculate the revenue at each vertex and hopefully come up with a maximum plan for this shop. Okay, so let's get started on that. Okay, so to graph this feasible region, it's a lot of inequality graphs to consider. We need the intersection of all of them and decide on a coordinate system that will fit everything. Let's sort of take this one at a time and think about graphing the boundary lines. First of all, these ones, x greater than or equal to 0, y greater than or equal to 0. That puts us in the first quadrant, basically, there. Okay, duly noted. Now, what about graphing boundary lines for each of these? I like to consider the intercepts, at least approximately, to see what sort of numbers I need to put on this coordinate system. If y is 0 here, x is going to be around 120 or so. If x is 0, y is going to be, divide that by 8, just roughly, okay, something around 50-ish. This one here, if y is 0, x is about 96. Y is 0, okay, 48. And this one, when y is 0, x is 84. Here, y will be around 60 or so. Okay, looks like x up to about 120 or so, and y up to about 60. I think we can get the graph all in order. If we go with 10 units per centimeter, I think will be effective. Big graph is good, right? Because you get more detail clarified that way. And so here on the x-axis, at least 12 centimeters. Okay, scale this up a tick mark per centimeter. Tick marks are going to be worth 10 apiece on this. Okay, for a y-axis, about 7 centimeters should be adequate. Okay. Let's do that scaling. So 10, 20, 40, 60, 20, 40, 60, 80, 100, 120. Okay. Alright, and labeling, what's on this axis here, for instance? Well, variable-wise, it's x. In an application problem, I like to try to use the worded description so that the reader looking at this doesn't have to think and decode what x is. And what is x anyway? This is the number of standard design grills. Okay, so here, number of standard design. Okay, and this axis, which is a variable, is y in our problem, but it is also the number of deluxe designs. Okay, now let's pick up a contrasting color and consider the first inequality we haven't worked with yet, and that's right here. Okay, let's graph the boundary line. If y is 0, 3x is 368, divide both sides by 3. X would be, let's see, 1, 2, doesn't divide evenly. Okay, 1, 2, and 2, 122 and 2/3. Okay, 122 and 2/3. There's 120, 122 and 2/3, right about there. I'm making sure I label these intercepts with their exact coordinates right now, because these could become vertices. Okay, and a point there. Back here. Alright, let's suppose x is 0. What about y? In the boundary line case, divide 368 by 8. Let's see, 4 times for 32. 4, 8, 48. 6 more times. Okay, 46. Right there would be 46. And now it's time to sketch in a solid line, because this is a or equals to type inequality. The equation of this boundary line is 3x plus 8y equaling 368. And as far as shading goes, just to keep track of things, not a heavy shading, but if we test 0, 0 into this inequality, 0 for x, 0 for y, that would make it true. So it's 0, 0 side of the line here that gets shaded. Alright, just kind of keep light track of that. And let's go to the second inequality that we have yet to graph the solutions for right here. Okay, if y is 0, for the boundary line, and imagine the equality case, that's the boundary line, and imagine this is an equality for a moment. If y is 0, we have x being 96. Okay, there's 90, 96, about there. And if we were to have, say, x be 0, 2y is 96, y would be, okay, 48. Okay, right here, let's be kind of careful. That's 46. There's 50 right in between. Okay, go 48 there. And now, the ruler for the boundary line, solid line. It's an or equals to type of inequality. Okay. And the equation that goes with this is the x plus 2y equaling 96. Okay. Time for a third contrasting color. And we go on to this inequality. Alright, suppose y were equal to 0. 2x is 168, y is 84. Okay. 80, there's 90, 84, about there. Now, for the boundary line, again, imagine this is an equality for a moment. If x is 0, 3y is 168. Y is 168 divided by 3. Let's see. 5 times for 15. 8 left over. 6. Okay, looks like 5, 6, 56. That's about here. Okay. A solid line for the boundary line. Okay, let's label this boundary line equation. That is the 2x plus 3y equaling 168. Okay, now that is everything. It looks, and by the way, as far as the shading goes, actually, we didn't discuss the red line's inequality. Let's back up for a minute. X plus 2y less than or equal to 96. Testing 0 is 0. Makes this true. Okay, for the red line, it is also bounding a region that's the 0, 0 side of the line there. The green line, which is the boundary line for this inequality, which side of the line gets the shading, testing 0, 0 here. 0, 0 makes this one true as well. Okay, everything is to this side of the their lines. This will leave us with an overall feasible region that is bounded by, well, here for starters. Now, right here, it's the blue line that bounds things up. Then the red line takes over as the boundary in this segment here. Okay, then it's the green line that forms the boundary right there, and of course the x-axis is one of the boundaries. Okay. Okay, so here we have our feasible region. Now a couple of important details still have yet to be resolved here. Okay, here is a vertex. I like these vertices to really be prominent, so I even use the circle template to make very prominent solid dots. Here back up here at 0.46, that ends up being a vertex. Of course, 0, 0. And out here at 84.0. Okay, now again, a couple details. We need this point here. Okay, well, as a kind of sub-calculation, I'll put an asterisk so that someone wondering where does this information comes from, they can be referred to, say, over here. And what is this? Blue line, red line intersection. Okay, blue line, 3x plus 8y equaling 368. And red line, x plus 2y equaling 96. Okay, this is ready for some elimination. First equation, minus 3 of the second. That will eliminate the x's. So x's are gone. 8y minus 3 times 2, or minus 6y, 2y. Okay, 368 minus 3 times 96. Okay, let's see. If we subtract, this is almost 100, so it would be like almost 300, but we give back 4, 8, 12. Okay, so if I subtracted 300, that'd be 68, give back 12, that puts us up to 80. Okay, so then this means y equals 40. How's this look for graphic consistency? Back over here, here's this vertex, 40 looking pretty good. Okay, keep going. The corresponding x, by back substituting, we can take the second equation, 96 minus 2y, 2 times 40 in this case, that would be 96 minus 80, we're down to 16. Is that graphically consistent? X coordinate here, yeah, around 16 looks fine. Okay, so we're confident this is indeed 1640 for that point there. Okay, let's go here. Another point to calculate. This will be 2 asterisks to refer the person to perhaps here. Now in this subcalculation, we need the intersection of the green line and the red line. Okay, green line, 2x plus 3y equals 168. And red line, x plus 2y equals 96. Okay, elimination method ready to go here. Let's say this equation minus 2 of these. Okay, x's are eliminated. Minus 2 of these, that would be minus 4y. Okay, negative y, the net result there. Okay, minus 2 of these. Okay, now let's see there. Okay, 2 of these, what would that be? 192. Since this number's bigger, let's do the 192 and subtract the 168 and then attach the negative sign. Okay, that's 4, that's 2, and that's gone. Okay, so we're looking at a negative 24 then. And so then y equals 24. How's that look as far as graphic consistency over here? Okay, here's 20, there's 30. In there, looks good. Okay, let's get the corresponding x. Let's recycle this second equation. It's the easiest. X would equal 96 minus 2 times y, 2 times 24, and that's 96 minus 48. No, it is 48. How's that look graphically? Here's this point. 48 looks alright. Okay, so this looks to be 48, 24. Okay, we got all our vertices. We are now ready to go and calculate the value of revenue at each vertex and find out how to make this company the largest possible sales revenue. Okay, so for our table here, we can take a vertex here and calculate the corresponding revenue here. Going back, looking at that originally formulated revenue function, we found it to be the 50x plus 90y. Okay, now let's go and take all our vertices. We got 0, 0. We got 84, 0. We have 48, 24. We have 1640, and we have 046. Okay, let's see, first here, this is an easy one, 0 plus 0, 0. Okay, second one, we get here 50 by 84 plus 0, 0 times 90, and to do this, you can just do 100 by 84 and divide it by 2. So that would be 8400 divided by 2, 4200. Okay. Next, at this vertex, we got to compute 50 by 48 plus 90 by 24. Okay, 50 by 48, again, just do 140 and then take half the result. So that would give us 4,800 and half, 2,400 plus 90 by 24. Okay, maybe do up here 9 by 24 and then add a 0 afterwards. So there's 36, 3, 216, 2160. Okay. Sums to 4560. Okay, this vertex, we've got to do 50 by 16 plus 90 by 40. Okay, here we're looking at 800 plus, here you can do 9 by 4, 36, add 2 zeros. Sum these two, we're up to 4,400. Okay, here we get 0, 50 by 0, and then it's plus the 90 by 46. What about that? Okay, let's do 9 by 46 and then add a 0. Okay, 54, carry the 5, 36, and 5, 41. Okay, add a 0. That puts us at 4150. Okay, let's examine for our maximum revenue. Okay, here we are. Make a conclusive statement now. What's this mean? A maximum sales revenue of, this is in dollars, 4,560 can be achieved by fabricating, okay, 48 for X. X was the number of standard design grills. Okay, so we can say 48 standard design grills and 24 deluxe design grills. Now, since this is the major conclusive statement of the whole problem, I want to make this really prominent. Bring a sort of a heavy black marker and a cloud to make this jump off the paper. And I would like to do some sort of check over of this because there really is a lot of room for error, and the most likely source of error is that formulation to begin with. The math, probably okay, but formulating is always the real skill in an application problem. And so let's try to come at this with something kind of fresh and different that doesn't use any of our existing equations here. Okay, so here's just one idea here. I just want to know if these 4824 are these kind of productions even sensible. Okay, maybe some mistake in the formulation, and everything here is just crazy. All right, let's do this. Let's see how much labor time overall in hours is required, approximately, to make a standard design grill. Okay, I'm looking back at the original statement of this whole problem, and let's do this. Labor for a standard design it's about equal to, let's see here, standard design, it says 22.5 minutes of fitting, 10 minutes of welding, 10 minutes of painting. Let's add those up together. Okay, 22.5, 32.5, 40. Okay, 42.5. About how many hours is that? 42.5 minutes. Okay, 3/4 hours. Okay, labor for a deluxe design about equals to, okay, I'm looking back at that deluxe design information, 60 minutes of fitting, 20 minutes of welding, that's 80 minutes, and 15 minutes of painting, 95 minutes. Okay, that's about 90 minutes. It's about an hour and a half. Okay, so 3/2 hours. Okay, so this means that if we're going to make 48 standard design grills, hold on, capital S. Requires about, we got 48 of them. They're at 3/4 an hour a piece. 3/4 of 48. Okay, we're looking at 36 hours there. This 24 standard deluxe design grill idea, what about that? 24 deluxe design grills requires approximately, alright, 24 of them, 3/2 of an hour a piece. That would be 36. 72 hours. So we're claiming some plan that overall is looking at around 72 hours of labor. The total available labor, this is all for one day, of course, approximately equals to, if needed, what have we got here? Back to the information. We have the fitters, 5 full-time, 1 part-time. Okay, this is easy to do pretty exactly. So we got 5 by 8 plus 1 by 6. And then we have these welders, 2 full-time at 8 hours. Okay, 2 by 8. And then there are 4 part-time painters, each at 3.5. 4 times 3.5. What's this equal to? 40. 46. 16 more. Let's see. 56, 62, and 14. 72, 76. Okay. 76 hours. Okay, so basically we've got enough time to do this in rough terms, just looking at the overall hours needed, the overall hours that we have. It's consistent, so we have the overall labor based on these two numbers here. Okay, just wanted to do something to keep us from having an absurd answer pan out, because after all this, it's hard to really tell until you take a look at the problem fresh and look at it from a physical sensibility standpoint. Okay, so at least it looks reasonable there. Now, as far as all the other small details here, again, so much, we're doing this manually, all kinds of arithmetic and that kind of thing, maybe some other mistakes. The other final check could be on this, it would be to actually just redo the problem another day so that you're not influenced by your first decision, and see that you get the same conclusion 2 times. That could be another check on detailed calculations. Okay, but at least for this, we are looking pretty good, and that's it.